Well, welcome back, everyone. Today we're going to start in on our last spectroscopy method, which is Proton Nmr. And we've already covered carbon-13 NMR. And good news, bad news. Good news is there's quite a lot that's very similar or even identical to carbon NMR. Bad news is there's a couple of things that are unique to proton NMR, and those things complicate the matter quite considerably, which is one of several reasons that I put off talking about proton NMR as long as I can possibly get away with. And of course, Bella's here to greet you all. She just wants to get on YouTube and to lick me with sandpaper and to be a pest because she's silly. Oh, goodness. Okay. So, what are some of the things that the two methods have in common? Well, recall that in all kinds of NMR, not just carbon or proton, but in NMR in general, it's a method that relies on radio waves, which are the lowest energy kind of electromagnetic radiation. Photons of radio waves causes a transition in atoms at the level of the nucleus. It causes the nuclei to undergo what are called spin flip transitions. And that's all because atomic nuclei have a property that makes them as if they were tiny rotating spheres. They're not, of course, but it's as if they were. So that's one thing that, that proton NMR and carbon NMR have in common. In proton NMR, we learned that we would expect one resonance for every chemically distinct type of carbon atom. And we went over how to tell whether two carbons were the same or different. Exactly the same idea in proton NMR. We expect one resonance for every chemically distinct type of hydrogen. And I've even given you, let's see, where is it? Bella's trying to lick me. Sometimes she gums me too, which is not terribly pleasant. Let's see, where were we? Yes, so in your class notes, I pointed out a place in my chapter 10 class notes from the first semester where I gave a step-by-step method for being able to tell whether two carbons are the same or different chemically for carbon NMR. You can use the same method for hydrogens as well. So you can check that in the chapter 10 class notes. That's way back when we were talking about halogenation of alkanes and trying to determine how many products were possible and whether this set of hydrogens and that set of hydrogens were the same as each other. It works the same way for proton NMR. Anyway, in that way, carbon and proton NMR are very much the same. Chemical shift is also a thing. We looked at a correlation table for carbon NMR. There is also a correlation table for proton NMR, which I'll comment on. It's in your book, but I'll comment on it in a little bit. But in carbon NMR, we learned that the chemical shift, where the resonance showed up on the chemical shift range, varied depending on how, among other things, how much electron density was or was not being withdrawn from that carbon atom by nearby atoms, usually electronegative atoms, oxygen, halogens, things like that. And but we saw a chemical shift varying on a scale between roughly 0 parts per million to, maybe as high as 210, 220 parts per million at the extreme downfield range. And it's the same idea for proton, except the chemical shift range is narrower because the energy of the radio waves used varies depending on what type of nucleus we're talking about. And so instead of 0 to 200 or 220, it'll be more like 0 to maybe 15, 14, usually not higher than 12. So it's a different range, but the same idea. Chemical shift is still a thing for proton NMR as well as for carbon NMR. And indeed, it's the same for any kind of NMR. You'll recall, I hope, that you can look at the periodic table and pretty much every element that at least is reasonably stable. You know, this I guess wouldn't apply if it's radioactive and has a half-life of 4 milliseconds or something like that. But other than that, every element in the periodic table should have at least one isotope that's NMR active. And that being said, I think none of you will be surprised to hear that organic chemists don't make too much use of vanadium NMR, because we're not making things with vanadium in them. We certainly are making things with carbon and hydrogen in them. So those are by far the most common methods used in organic chemistry. I think they're the only ones worth learning for students taking a 2-semester survey course of organic chemistry. But there are certainly other methods. I've had some experience taking boron 11 NMR, works very nicely. Dr. Pennington, I know, when he was in grad school, when I was taking boron NMRs, he was taking deuterium NMRs, because deuterium is hydrogen 2. Remember that in order to be NMR active, a nucleus must have either an odd atomic number, in which case all of its isotopes are NMR active, and that's the case for hydrogen. Hydrogen is element 1. So all hydrogen isotopes are NMR active, and you can take spectra using them. If the atomic number is even, then the mass number needs to be odd. So that's why carbon 12 NMR is not a thing. It's element number 6, and so carbon 12 is an even mass number, so that's not going to work. That's why we need to use carbon 13. But other than that, there are other ones that are used. Phosphorus Nmr is done quite a bit if people make compounds with phosphorus in them. Same thing for fluorine 19 NMR if they're making fluorinated compounds. I've even heard of silicon 29 NMR if people are working with silicon. But proton and carbon, I think, comprise the vast majority of the NMR spectra that are taken today. You may also recall that the guts, if you will, of an NMR spectrometer and the guts of an MRI instrument, magnetic resonance imaging, are the same thing. It's essentially the same method. All that differs is how the data is worked up. But as you can imagine, we need to avoid using scary words like nuclear for public relations issues in something like that that's going to be used in a widespread manner on patients. So that's why. But the internal workings are essentially the same. Another thing, another factor by which carbon and proton NMR are the same is they both use an internal standard by which all of the chemical shifts are set relative to it. And in carbon NMR, we used tetramethylsilane, which is a silicon atom with 4 methyl groups on it. And all 4 of those carbon atoms are the same chemically. So we define the chemical shift of tetramethylsilane at 0 parts per million for carbon NMR. And we use the same internal standard for proton NMR, actually, almost always. In this case, all 12 of those hydrogens are chemically equivalent. And so we, by definition, we set that at 0 parts per million. And generally, the instrument nowadays does that for us. And sometimes it needs a little bit of help. But this is why, as you look at proton NMR spectra, you might see a peak at 0 parts per million. That's your tetramethylsilane. That's your internal standard. So those are the ways in which carbon and proton NMR are the same. There's 2 major differences that are called peak integration and spin-spin splitting. And that's what we're mainly going to focus on today. We have 2 classes to cover proton NMR, and I think we'll pretty much need them. I had made some re-polling questions at the last minute for today. We didn't get to them in the last class, and I don't know that they were all that good anyway, so it's probably no great loss. But in any case, please do register your attendance. I want to be sure everyone at least gets credit for being here. Good. So what I propose to do is pretty similar to what we did with carbon NMR. I'm just going to show you a bunch of spectra, and honestly, starting with very simple ones, and they'll get progressively more complicated. And honestly, that's the best advice I can give you guys too. The most valuable practice you can get in is just by looking at and analyzing as far as you can all of the spectra that you can. And if you go to that website that I gave you guys at the beginning of the semester, you'll find as many spectra as you want to. You can search by name, you can search by molecular formula. I like to search by molecular formula because you'll get all the different possibilities. Some will be very simple, some will be rather outrageous, but most of the Proton Nmr spectra should be recorded. And I often use that website to get spectra for exam problems. The other thing that I sometimes use is ChemDraw also can calculate NMR spectra. It's not the same thing, of course. It's you can't submit them with your journal article and say you took the spectrum. You know, these are calculated, but it does a pretty good job. I've done at least one of them, and you'll see it works actually pretty well. Good. So about that correlation table, there's a correlation table of chemical shift ranges for Proton Nmr in your textbook, and or in normal semesters where exams are not open book, I always say that I do not recommend that you memorize that table. I don't think that's a good use of your time because all of those figures in that table are just guidelines. It's just meant to say maybe 85+% of the time protons of this type show up in this range. That's the most you can get out of it. On top of it, if you want to have that correlation table at the ready for exam 4 and the final exam, you can do that. I don't even know that I necessarily recommend that. My hope is that you will not even look at it, at least not very much. You will get a lot more out of looking at actual spectra. That will give you the knowledge that you need to solve problems, so you don't need to waste time looking up every single thing. So, so that would be my recommendation, is just get in there and look at Proton Nmr spectra. You know, maybe don't start with cholesterol. You know, start with something nice like 1-bromopropane, or, you know, start with 3 or 4 carbons and maybe get progressively more complicated. I'm not going to commit to an exact number of carbons that your molecules will have. 20 is probably too many. You know, 10 even might be pushing it. 3 is probably not enough, but certainly reasonable. Good. So so let's get right into it with peak integration. This is a method by which the spectrometer literally integrates, finds the area underneath the resonances, between the resonances and the baseline. And we didn't really use that in carbon NMR because almost always nowadays, and certainly it was the case for us, all of the carbon NMR spectra we looked at were what they call broadband decoupled, which is a method that more or less makes peak integration useless, among a lot of other things, but it also simplifies the spectra a tremendous amount. So there's a huge payoff for that. But in Proton NMR, we use the area under each of the resonance, and it turns out to be proportional to the number of protons that the resonance represents. I didn't say equal to, I said proportional to. And the instrument takes care of all that for us. It normalizes everything to the smallest possible, to the smallest of all of the integrals. It divides through by that smallest number, and the numbers that pop out are then going to be proportional to. It's all going to be about ratios. They're proportional to the number of hydrogens in the resonance. Now, the height of the peak doesn't matter, because that can vary, because you might have a tall, skinny peak and a broader, shorter peak that have the same area. So the height of the peak doesn't usually mean a whole lot, but the integral does mean something. It's going to be proportional to the number of hydrogens that are in that resonance. So I'm going to start with some pretty simple Proton Nmr spectra. The first one is of Chloromethylmethyl Ether, which is this compound over here. And I think looking at that, you'll agree with me. There's two types of hydrogen. There's the 3 and the CH3 that are the same as each other. And the 2 and the CH2 are the same as each other, but these two are different from one another. As I look at that structure, well, as we look at that structure, what would we expect to see? Well, we'd see two resonances, certainly, because there's two types of hydrogen. I'd expect that the CH3 protons would show up maybe round about 3.5 or 4. That's usually where protons show up when they're alpha to oxygen like that. Meanwhile, these CH2 protons are alpha not only to oxygen, but also to chlorine. So you'll have both effects pulling that resonance downfield. Remember, the more downfield the peak is, the more to the left, or the more downfield the peak is. In general, it's sort of a rough approximation, but in general, the more electron density is being withdrawn from that nucleus. And so I would expect, the sky's the limit for this one, I would expect it to be at like 5.5 or 6, so to be pulled pretty far downfield, which is why you don't want to depend on that correlation table too much, by the way. If you look at that correlation table, I guarantee you it will tell you that a peak at 5.5 or 6 parts per million is vinylic. But there are no vinylic hydrogens in this compound. You see, it's just a guideline. So, glance at it from time to time. Certainly make use of it while you're working on your allo questions, by all means. But please don't rely on it to get you through. You're much better off looking at a bunch of actual spectra. Anyway, let's see what we have. And just as we said, we have two resonances. The integrals here are given for us. This is the way I usually like to report integrals. But this doesn't tell us right off the bat whether it's literally 2 H's and 3 H's. It could be 4 to 6. It could be 3 to 9. It's just the ratio. It's only the relative number. Now, as it turns out in this particular case, it is 2 H's and 3 H's. But if the compound instead had 4 of one type and 6 of another type, you would still see 2H and 3H. It only gives you the ratio, not the absolute number of hydrogens. So furthermore, just as we expected, our 3H resonance is for this methyl group because there's 3 H's there. And that's at, almost exactly 3.5 parts per million. The other one is way up here at about 5.4, 5.5 parts per million. And that's going to be the CH2 resonance that's pulled downfield extra by being between the oxygen and the chlorine. But other than that, this spectrum, I think you'll agree with me, is entirely consistent with that structure. We expected and found two types of hydrogen. We expected them to be in 3:2 ratio. Indeed, they are. And the chemical shifts make sense as well. I have one more relatively easy spectrum to go on. Of course, always feel free to ask questions. I think that might almost be better. I'm starting to think. I could be wrong about this, but then me going, are there any questions? And then awkward silence, during which time everyone went, eek, and oh yes, I had a question, but I just forgot it, So just because I don't ask if there are questions doesn't mean I don't care about your questions. Liz was coded for the lab for it. You've already done Proton Nmr? Because I know you did IR last term. IR is pretty simple. That is one disadvantage of my putting off the Proton Nmr, I will admit. But I do have reasons for it. One of them is to avoid all this peak integration and spin-spin splitting stuff. Because learning all of that at once, that's a lot of stuff. And the other reason that it's to your benefit to put this off is because you get to be reminded about NMR here as we're getting closer to the final exam. So it's good to review all that. So there's good and there's bad. And I realize I'm not going to make everyone happy, but But anyway, let's do our next relatively simple one. This one is methyl acetate. Methyl acetate is this compound over here. It's the methyl ester of acetic acid. And if you've read ahead on this, or if you know something about spin splitting, then you see why I picked those two, because I did it knowing we're not going to get any splitting. But in any case, I think you'll agree with me that there's two types of hydrogens. There's this methyl here, that's alpha to the carbonyl. Protons of that type are generally about 2.5, somewhere in that range. And the methyl group that's attached to the oxygen, so those two methyl groups are different. And so this one, again, I would guess 3.5 or 4, give or take. So I would expect to see two resonances of equal integrals that show up at those two places, one at about 2.5 and one at about 4. And lo and behold, that's exactly what we've got. So again, notice the height of the peak doesn't mean anything necessarily, not for singlet peaks. I would guess that this peak is just a little sharper and this one's a little bit broader, and so that's why they differ in height. But they have the same integral. And again, notice it doesn't say 3H3H. We don't get that information. All we get out of it is that it's the same number of hydrogens for both of them. So, but since they're both 3H resonances, they come out with the same integral. And just as we said, this one's at about 2.1. That's right on the money for protons that are alpha to a carbonyl. And this one here is at about 3.7, very typical range for protons that are alpha to oxygen. So far so good. And if we stopped here, Proton Nmr would be very easy. But we need to get to the spin-spin splitting also. But like I said, this is the way I usually like to report integrals. Just again, bear in mind, they're not exact numbers. They've been normalized already for you, but they're not exact numbers. They're just ratios. There are other ways of reporting integrals. You'll get to see some of them in the OWL assignment. I won't give you my solemn word that I will always and only report integrals like this. There are other ways to show them. But I do like using this method in those cases where I feel you need the integrals in order to solve the problem. Sometimes you might not need to. Sometimes the spectrum's easy enough without it. I should also mention all of these spectra in the class notes are from that one website that I recommended to you guys. Don't be intimidated that it comes from Japan. There is an English version. I think the link I gave you will take you to the English version. Good. So far so good, but we need to get also to spin-spin splitting. And I would like to at least cover the simpler types of cases, at least those cases that will get you, at least enough information to get you through 80% of the cases, maybe 85, certainly the simplest cases. And I've described how this works, and the phenomenon of spin-spin splitting or spin coupling comes from, again, this idea that nuclei have this spin quantum number thing. And so if you have nearby nuclei, their spins could align or could be against one another. And if there's 3 of them, there could be all different, and we could draw wonderful diagrams to describe all this. As you know, I like to keep things very results oriented. I mean, that material's there in the textbook if you want to refer to it to get some idea of where all this comes from. But I'd rather I like to cut straight to the chase. I did give you a step-by-step method for figuring out how many peaks to expect a resonance to split into. I don't think I can make it any more step-by-step than I did here. No, oh well. Okay, so and I'll demonstrate how this works. So the first compound I want to look at is 1,1-dichloroethane, which is this compound over here. And I think we would expect to see 2 resonances, one for this unique hydrogen that's between the chlorines, that's alpha to both chlorines, and one for the methyl group. And I think indeed we'd also expect to see a 3-to-1 ratio, right? Because it's a CH3 versus a hydrogen. And so far so good. That's exactly what we've got. We've got a 3H resonance here at about 2 parts per million because this carbon is just attached to another carbon, granted a fairly electron poor carbon. Usually alkyl hydrogens are more like 1, maybe 1.5. This is pulled down a little bit by the 2 chlorines being nearby, but not nearly as far as we'd expect that resonance to show up, because it's alpha to not 1 but 2 chlorines. So again, that one might be as high as 6. What is it? Yeah, it is almost 6 parts per million. If there were just 1 chlorine, I'd expect the resonance to show up in pretty much the same range as for oxygen, somewhere between round and about 3 and 4. But since there's 2 of them, it gets pulled down even further. But in terms of the integrations and the chemical shifts, no big surprises yet. The surprise is this splitting. And so that's where it comes from. Essentially, the way it works is, and again, there's your step-by-step method that you can use to calculate simple splitting. I don't think you'll need a calculator on this exam. I think you can count on your fingers. You know, you don't need a calculator to add 1 to numbers. But let's consider, for example, this red hydrogen. And let's say that we're looking at the resonance for that red hydrogen, which we already know is down here at almost 6 parts per million. What the step-by-step method tells you to do, why does it get pulled down? Downfield, you mean? It's because chlorine is so electronegative and it's withdrawing electron density. And so the more de-shielded of electron density the nucleus is, the further downfield it goes. The more shielded it is, the more electron density that it has, the more upfield it is, the more to the right. Now, why that is, fundamentally, I don't think we really know. I certainly don't. There's some interesting theories, but I don't think we really know why this is electron poor and this is electron rich. But that's essentially that pattern usually gets followed. Is that what you meant? If I get pulled downfield chemical shift? That's the best I can do. Yeah, it did. The pattern usually holds. It's not absolutely perfect, but it usually holds. Good. Well, yeah, good. So we're looking at the resonance for that red hydrogen over here. And what can we expect to see? Well, in order to know how many peaks to expect, you need to count the adjacent protons. That is, protons that are on the carbon next door, and add 1. So there are 3 protons adjacent to that red proton. 3 plus 1 is 4. So we would expect to get a quartet of peaks. And that's usually how I will say what the multiplicity looks like, or D for doublet, Q for quartet. In cases like this where we can't really see the splitting so well, actually, that would be a good one to, I'm going to get hate mail for this. But let's calculate that spectrum and see if the spin-spin splitting is a little easier to see. There we are. Oh, what do you know? That's much nicer. See how much easier it is to see this doublet in this quartet. So that's why I will how did it do in the chemical shifts? 5 point, it's a little low on the quartet, and a little bit high on the doublet maybe, but not bad considering it's not measuring it, it's calculating it. So it's pretty good. Be that as it may, so that's why sometimes I will use ChemDraw spectra instead of these. Just if it sometimes comes out easier to read if I calculate them in ChemDraw, and it will come out pretty much the same. Good, so let me go back to my original window. Good, so what we're saying is there's 3 protons adjacent to the red proton. 3 plus 1 is 4, so we expect 4 peaks, which are of different heights. I'll explain that in a moment also. As I said, the height of singlet peaks doesn't really mean anything, but you can get something from the relative heights in the multiplets, or rather they can be explained at least. Meanwhile, the 3H resonance is a doublet. So we're looking at the resonance for those 3 hydrogens, those blue hydrogens. And what we do is we look next door and we count 1 hydrogen next door. 1 plus 1 is 2. And indeed, we see 2 peaks here. So that's the nature of spin-spin splitting. And it's something you guys are going to have to practice a lot. It is, I've made it as simple as I know how to. I don't know how to make it any more step-by-step than this. And, you know, can splitting be even worse than this? Yes, that's why I wrote at least m+1 and at least n+1 peaks here. It can be worse than that, and we'll look at some examples of that on Monday. But I think this will get you through the vast majority of the times. Most of the time, the splitting will be relatively simple. It will be what we call first-order splitting. And that's certainly what we see here. And, you know, I don't intend to be unfair. In a case like this, if this spectrum had been an exam, I would have said D for doublet and Q for quartet. Or I might well have used, instead of using the actual collected spectrum, I might have just used the calculated spectrum because it was so much easier to see. That's a different one. Yeah, and that's so much nicer. You can easily see that it's a doublet and a quartet. I would probably still put D and Q for doublet and quartet, but it's a little, those are sometimes neater. I don't think they're using a very modern instrument for the spectra that they have on that one website. Good, so we'll do at least another couple examples of this. But that's the nature of spin-spin splitting. Now, what about the relative heights of the peaks in the multiplet? That you can get from Pascal's triangle, which you probably heard about in one of your high school math classes. And Pascal's triangle is generated by putting essentially ones all down the sides of a triangle. And then the numbers in the middle are decided by adding the 2 numbers immediately above to the left and to the right. So you get 1, 2, 1, and then 1, 3, 3, 1, right? 1 plus 2 is 3, 1, 4, 6, 4, 1. Next one would be 1, 5, 10, 10, 5, 1. And Pascal's triangle rears its head in a lot of places. In math class, you probably used it to expand, are they called binomials or polynomials? Powers of x plus y. So if you square x plus y, you can use now these coefficients. X squared plus 2xy plus y squared. If you cube x plus y, you get x cubed plus what? 3xy squared plus 3x squared y plus a y cubed, and so on and so forth. If you did to the 4th power, you'd use those. So it gets a lot of uses, and it's used here too. Now, it's not exactly perfect. You'll see that those 2 taller peaks are not exactly the same height. Likewise, these 2 probably aren't, but it will be pretty close. There are other things that affect the shape of the peak than Pascal's triangle, but Pascal's triangle is good for population things like this because it comes from, as I said, all the different ways that all the different protons can have splitting or can have spins relative to each other. And I should stop doing too much with my fingers because it gets inappropriate. Anyway, you get the idea. Let's look at another one. Again, you're gonna have to practice this. It's okay if you walk out of class today not understanding this entirely. But I at least want to give you enough information to get you started so that you know how to analyze it and what to look for. Next one is ethyl acetate. So we've gone from the ethyl ester of acetic acid to the methyl ester of acetic acid. And I think you'll agree with me that we'd expect to see 3 types of hydrogens. There's this methyl group that's alpha to the carbonyl. There's this other methyl group, which is different. It's attached to the CH2. And then, of course, the CH2 protons. So we'd expect 3 resonances. We'd expect them to be in a ratio of 3 to 3 to 2. And that's exactly what we have. We have 2 3H resonances, which are our 2 methyl groups. And we have that 2H resonance. So we already know this resonance has to be for the CH2. Meanwhile, even apart from the splitting, I think we can tell that this resonance must be for the CH3 that's alpha to the carbonyl. 2 to 2.5 parts per million is a very typical range for protons of that type to show up. Meanwhile, the other methyl group is closer to 1 part per million. That's very common for just regular alkyl type hydrogens. So even apart from the spin-spin splitting, we can figure out what corresponds to what. However, the splitting is also helpful, and actually in this case, it's very nice and easy to see. So I still mark them singlet, quartet, triplet, but it's very easy to see then. So once again, let's look first at this resonance. Well, I think you'll agree those hydrogens have no adjacent protons, right? There's no hydrogens on the carbonyl carbon. And the adding one rule still works. 0 plus 1 is 1. So there's just one peak. So if there's no adjacent protons, you'll just get a singlet resonance. And that, by the way, is how I cheated with these first ones. I just was careful to pick two compounds that in which none of the protons had any adjacent protons. That's how we got only singlets. So, but that still works also. Meanwhile, let's consider this other methyl group, which I've colored blue over here. This methyl group, its resonance, the resonance for that methyl group is going to be affected by the two hydrogens next door to it. Those two are going to do the splitting. The red hydrogens are going to split the blue ones, and the blue ones are going to split the red ones. So since there are two red hydrogens, 2 plus 1 is 3, that means we expect to see a triplet resonance for that methyl group. And indeed we do. There's 3 lines here. Meanwhile, the red protons have 3 adjacent protons. The 3 blue protons will split the 2 red protons. And so 3 plus 1 is 4. We'd expect the resonance for the CH2 to be split into 4 peaks. And indeed it is. And I think it should be 1 to 3 to 3 to 1 by Pascal's triangle. I think you'll agree that's close. It's not exactly perfect. Likewise, 1 to 2 to 1. It's close. Will a singlet only occur if there are no adjacent protons in the structure? Yes, I think so. I can't come up with any other way. I think that will generally be the case. I don't have exceptions popping up in my head. But notice that it's not even really an exception, right? Because you still add 1 to the number of adjacent protons. And if the number of adjacent protons is 0, 0 plus 1 is 1. So the rule still works. The rule breakers will come next time when we see more complicated examples of splitting. So we have 10 minutes left. Any other questions, by the way, just chime in on chat or unmute yourself, that's fine. I think we might be able to do 1 or 2 more of these. We're still gonna stick to first order splitting. We're not gonna get to any of the ugly stuff. So we did ethyl acetate. Next one is diisopropyl ether. Diisopropyl ether looks like that. And I think you'll agree there's 2 types of hydrogens. There's this unique hydrogen here. Well, there's one in the other side. That's on the isopropyl group. So you have 2 of that type. And then you have 4 methyl groups that are all the same that I've covered, that I've colored blue. And so the ratio would be 2 to 12 or 1 to 6. And by the way, already we can see that's the case. We have a 1H resonance and a 6H resonance. In terms of chemical shift, what would we expect for the 12 equivalent? Are we going to be matching spectra to compounds or drawing compounds from spectra? Either. Both are fair. I've put old exams up, so both are possible. But again, I can't commit beforehand to this or that type of format. But both are certainly fair game. I mean, you'd have to be given enough information, of course. I wouldn't give you something if I thought there wasn't enough information. So anyway, all 12 of these hydrogens are the same. And where would they show up? Well, those hydrogens are attached to, these 2 methyl groups are just attached to another carbon. Granted, that carbon itself is attached to oxygen, but these shouldn't be too far out of the regular chemical shift range for alkanes. And indeed, they're at about 1.2 parts per million. That's very typical for just alkyl type hydrogens. These protons, though, that one is on a carbon that's alpha to oxygen. And we've already seen protons alpha to oxygen at round and about 3.5 or 4. And indeed, that is where it shows up, right about 3.6. So the chemical shifts match up. The integrals match up. What about the splitting? Well, let's consider the resonance for this one red hydrogen. I think you'll agree that next door to it are 6 hydrogens, no fewer than 6. So 6 plus 1 is 7. That means we would expect to see 7 lines, and we do. If you really stare at it, you might even just be able to pick out all 7. You can just barely see them all. It's just a little bit low resolution. Meanwhile, the methyls will now be split into a doublet because there's one adjacent proton. So the red proton, by virtue of being next door to them, splits the blue protons into a doublet, and the 6 blue protons split the red proton into a septet, seven lines. And that's indeed exactly what we see. I calculated this spectrum too, and indeed it's again much easier to see. So this might be a case where if I had put this problem on an exam, I probably would have wanted to use this one because it's much easier to see. I'd probably still point out that this is a doublet, and I would still point out that this is 7 lines, a septet. It's very difficult to see those last 2 peaks. I can just barely see the outermost 2 peaks. But ChemDraw does a pretty good job at calculating these things. So where are we at? 12:44. Let's do one more. We still have 6 minutes. Let's do one with an aromatic ring. This one, and then in fact, we'll calculate that one as well and see how we do. So P-N-acaldehyde, that is benzaldehyde with a methoxy group in the para position. So and aldehyde functional group over here. So C double bond O H. So that's P-N-acaldehyde. So let's see, how many types of hydrogen do we have? Well, there's the unique aldehyde hydrogen, of course. That's going to be pretty far downfield. Those usually show up around in about 9 or 10 parts per million. There's these 2 that are ortho to the aldehyde group. There's these 2 that are ortho to the methoxy. And then there's the 3 in the methoxy group. So I think we're going to be looking at 1 to 2 to 2 to 3 in terms of the relative amounts. And that's what we have. We have our 1H resonance. That's going to be our aldehyde hydrogen. The 3H resonance is also going to be a singlet because, again, if you look at that methyl group, there are no adjacent hydrogens. They would be coming right off the oxygen, and there are none. So no surprise that the aldehyde hydrogen and the methyl hydrogen are both singlet resonances. But what about these aromatic hydrogens? Let's do our blue versus red thing again. The 3H one is a singlet. Why is there a second small peak at the bottom of it? Those are just probably spinning sidebands. I usually on exams am very careful to put X's over peaks that you should ignore. Or I've even been known to edit the spectrum in a paint program because I know how easily students are distracted by that. Although, even if I had forgotten, the way you would know to ignore those peaks is because they're so small relative to these, right? If you had like a triplet resonance, you'd expect to see 1 to 2 to 1. This is like 1 to 30 to 1. So that's how you will know. If you see ones that are very, very small like that, then likely you'll be able to ignore them. So does that give you at least some information about what you'll have to know and what you might be given? Hopefully that helps a little. But that probably is the fault of the operator in not setting up the spectrometer properly. So we'll do red versus blue again. There's this type of hydrogen and this type of hydrogen. And I think in each case, you'll see the blue hydrogen has 1 adjacent hydrogen. The red hydrogen is 1 adjacent hydrogen also. And it will leave the same on the other side, by the way. So we would expect each of them to split the other one into a doublet. The red proton splits the blue proton, and the blue proton splits the red proton. And that's exactly what we have. We have two doublets. They're a little bit hard to see here. But let's talk chemical shifts before we calculate the spectrum. The methoxy, again, those are hydrogens alpha to oxygen. This, what do you want to call that? 3.8, very typical place for those. Aromatic hydrogens generally are round and about in the 7 to 8 range, 6.5 to 8.5 maybe. And yeah, that's where they are. So that's very typical for aromatic hydrogens. And then as I said, the aldehyde hydrogen, here we're at about 9.8, very, very typical. Exactly where I would have expected it to show up. For my last trick, let's end today by calculating this spectrum also. And we'll see how well ChemDraw does. Let's compare chemical shifts, and let's see how easy it is to see the splitting. There we go. Well, it's not a whole lot better, is it? But man, it absolutely nailed those chemical shifts. Look at it. So that's really astonishing. Again, I want to stress, this is doing it by pure computation alone. It's not looking at any experimental data. It's just calculating it. It's making an approximation. It did pretty damn well, if you don't mind my putting it that way. So I don't see any significant advantage, I guess, except now this peak's a little cleaner, right? We don't have the spinning sidebands over here. Good. So that, I think, is a good place to stop. We'll finish up talking about the simpler types of splitting and also get into the more complicated types on Monday. So have a great weekend. I'm happy to answer any questions. I can't stay forever because I have an appointment at 1:30, but if there are any immediate questions, I'm happy to take them. Other than that, have a great weekend.